So in the last class, we have seen how to find an initial basic feasible solution of a transportation problem using northwest corner rule. And for this given problem, we have seen that the cost regarding the initial basic feasible solution x11 equals to 1 2, x12 equals to 4, x22 equals to 10, x23 equals to 2, x33 equals to 7 and x34 equals to 8 is 200. It was wrongly reported as 218. It will actually be 226. And today we shall be studying some new methods to find initial basic feasible solution of transportation problem. Let us consider the same transportation problem, and we shall be solving this transportation problem using a method known as the matrix minima method. Matrix minima method. In matrix minima, instead of starting from the northwestmost corner, we start allocating from the cell in which the cost is minimum. As we see in the cost matrix, the minimum cost occurs at the 2-4 cell, which is 1. So we shall make our first allocation at this cell 2-4, and as we see, the maximum possible allocation at the cell 2-4 is 8, since the demand is 8 units and the supply is 12 units here. So after allocating 8 units at the cell 2-4, the demand will be fulfilled and supply will still be available 4 units from O2. So as before, we discard the column 4 as there is no need to allocate at any other cell in that column. Again, from the reduced cost matrix, we find the minimum cost, and we see that occurs at 2 cells, that is the 2-1 cell and 3-3 cell, and we can make allocation at either of these 2 cells. So if we choose the 2-1 cell, then the maximum possible allocation at the 2-1 cell is 4, and so the supply 4 has been now exhausted and the demand 12 has now been reduced to 8, and so we discard the second row now. Again we repeat the process, that is, we find the minimum from the reduced cost matrix, and we see that the minimum cost now is 2, which occurs at the cell 3-3. So we make allocation at the cell 3-3. Maximum possible allocation is 9, demand is fulfilled, supply available is 6 unit now, and we then discard the column D3, and we now have the cost matrix of 2x2 size, where the minimum cost is 4 units, 4 per unit item, and that occurs at the 1-1 cell, and where the maximum possible allocation is 8 units. Demand at D1 has been fulfilled, supply at O1 has been reduced to 8, and we discard the column D1. And finally, in the D2 column, we make our allocations 8 and 6, as only those are the remaining cells. So using the matrix minima method, our initial solution is x11 equals to 8, x12 equals to 8, x21 equals to 4, x24 equals to 8, x32 equals to 6 and x33 equals to 9. x33 equals to 9. So the total cost eight into 4 plus 8 into 6 plus 4 into 2 plus 8 into 1 plus 6 into 7 plus 9 into 2, that is equal to how much? 32 plus 48, that is 80. 80 plus 8, 88 plus 8, 96. 96 plus 42, 96 plus 42, 138. 138 plus 18, so it is 156. So we see that for this initial BFS the cost has been reduced, cost is lesser than the solution obtained in northwest corner rule. So we may expect that this may be the optimal solution, but to be confirmed whether it is the optimal solution or not, we have to find the net evaluations as earlier, but we are not doing it. We rather find initial basic feasible solution through another method known as the Vogel's approximation method, and which is believed to give the optimal solution quickly. So it is Vogel's approximation method, VAM in short. Here in each row and in each column we find the difference between the minimum cost and the second minimum cost. So in the first row we see the minimum cost is 4 and the next minimum cost is 6, so the difference is 2. In the second row minimum cost is 1 and the second minimum cost is 2 and the difference is 1. Similarly in the third row minimum cost is 2 and the second minimum cost is 5 and the difference is 3. Here one thing we have to note that if we choose 5 and 7 then the difference is 2, which is less than 3, but we have to choose the minimum cost and the second minimum cost and to find the difference. Similarly in each column we get the differences at 2, here 0, here 2 and here 8. And now we will choose the row or column corresponding to the maximum difference which we have just obtained, and we see that the maximum difference obtained is 8, which corresponding to column 4. So we will make allocation in the column 4, and in which column of in which cell of the column 4 will make our allocation, it depends on the minimum value in the corresponding column. As we see in the fourth column the costs are respectively 15, 1 and 9, so minimum is 1 and we make our allocation in the cell 2, 4 corresponding to the minimum cost 1, and we see the maximum possible allocation here is 8, so 8 is finished demand fulfilled, and 12 reduces to 4, and what, and D4 will now be discarded. Now from this reduced matrix we repeat the process again, that is, we find the differences between smallest cost and next smallest cost in each row and column. So in the first row it is 2, in the first row it is still 2, in the second row it is 2, earlier it was 1, now it is 2, difference between 2 and 4. In the third column it is third row it is 3, in the first column it is 2, it will be 0, and it will be 2 as earlier. And we see in this stage the maximum difference corresponds to the third row, and in the third row the minimum cost is in the cell 33, corresponding to the cost 2. So we make the allocation at the 33 cell, where maximum possible allocation is 9, so that 9 has been exhausted and 15 has been reduced to 6, and we discard the third column. Again, in the reduced cost matrix we again find the differences between the smallest cost and next smallest cost in each row and column. Here it is 2, here it is 4, here it is 2, here it is 2, and here it is 0. So the maximum difference occurs in the second row, and in the second row the minimum cost is 2, this one, because we have already made allocation in the cell 2, 4, and that column has already been discarded, so that will not be considered anymore. So at the cell 2, 1 we make our next allocation, and the maximum possible allocation at this cell is 4 units only. So this one will be exhausted, and demand will still be 8 units at D1. And so now we discard the second row, and in the next reduced matrix we again find the differences. It is 2, it is 2, it is 1, and it is 1. So we can make allocation at either the first row or the third row, that is O1 or O3. In O1 the minimum cost is 4, corresponding to the cell 1, 1. We make allocation here, and maximum possible allocation is 8. So the demand at D1 is fulfilled now, and supply remains 8. So we discard D1 now. We have only 2 cells remaining, 6 and 7, where we distribute the remaining supplies and demands accordingly, and we see we can allocate here 8 and allocate 6 here, so that everything has now been exhausted. So using Vogel's approximation method, okay, I wrote it for the net evaluation, we will do it later. better I delete it. Delete this table now. I'm sorry. Yes, let's write the solution we have just obtained. Yes, it is x11 equals to 8, x12 equals to 8 also, x21 equals to 4, x24 equals to 8, x32 equals to 6, and x33 equals to 9. And so we have the cost. We have the cost 8 into 4 plus 8 into 6 plus 4 into 2 plus 8 into 1 plus 6 into 7 plus 9 into 2 equals to. Have we got the same solution as in the matrix minima? Let's check. 8, 4, 8, 6, 9. Oh yes, we got the same solution as in the matrix minima method. So the total cost is 156 here also. Now we find the net evaluations. Yes, we'll do it here. As we have seen earlier, we will not consider the supply and demands here. Rather, I am writing the solution first. 8 here, 8 here, then 4, 8, 6, 9. Sorry. 4, 8, 6 and 9. We will find UI and VJs. We see in each rows there are two allocations, so we can choose arbitrarily any UI as 0. Let's take U1 equal to 0. So for the allocated cells 1, 1 and 1, 2, UI plus Vj will be equals to Cij. So V1 will be equals to 4 and V2 will be equals to 6. And as soon as V1 becomes 4, U2 will become minus 2, as in the allocated cell 2, 1 the cost is 2. So 4 minus 2 will be 2, and since V2 has become 6, it will become 1, since 6 plus 1 equal to 7 in the cell 3 2. Similarly, for the cell 3 3, we shall have V3 equals to 1, as U3 plus V3 should be equal to 2, and finally V4 will be 3, as for the cell 2 4, 3 minus 2 will be equal to 1. And now we find the delta ij's. The net evaluation delta ij's equals to Uy plus Vj minus Cij for the unallocated cells. First two are allocated cells, so in the cell 1 3 we have net evaluation equal to 1 plus 0 minus 9, so it is minus 8. In the 1 4 cell it is 3 plus 0 minus 15, it is minus 12. In the 2 2 cell it is 6 minus 2 minus 6, that is equal to minus 2, and it is in the next cell 1 minus 2 minus 4, that is minus 5. In the cell 3 1 it is 4 plus 1 minus 5, it is 0, and in the last cell 3 4 it is 3 plus 1 minus 9, so it is minus 5. As we see, all the net evaluations are less equal to 0, and our problem was to find the minimum cost, so we have got an optimal solution. So for the given problem we shall not be able to find any solution where the cost will be less than 156. We now see how an initial basic feasible solution can be improved to get the optimal solution. We consider here the problem what we were dealing with, and the initial basic feasible solution what we have obtained using the northwest corner rule. As we set the rule to find delta ij's as Ui plus Vj minus Cij, and the problem was to minimize the transportation cost, so the optimality condition was delta ij less than equal to 0, and we see that in the net evaluation two cells, namely 2 1 and 2 4, are at positive values, and of these two cells 2 4 has a value 10, which is maximum positive. So to improve the solution we will make some allocation at the 2 4 cell. We now consider only the allocations instead of the net evaluations, as in the next table here. Yes, we will make some allocation in the 2 4 cell. Suppose we make the allocation theta here. So if we make the allocation theta here, then along the rows and the columns theta is to be adjusted, because the supply from the origin O2 was total 12. If we allocate theta in the cell 2 4, then the total supply at O2 becomes 12 plus theta, so we have to adjust it. Also the demand in the fourth column has become 8 plus theta, so we have also to adjust it. What we do, we actually try to find a cycle of this kind. Yes, we will have to find a cycle so that each of the corners will be occupied by some allocated cells. So we can have the adjustment as 2 minus theta here, 7 plus theta here, and 8 minus theta here, so that the total supply and demands remains same. So the new allocations at the 2-3 cell is 2 minus theta, the 2-4 cell is theta, 3-3 cell is 7 plus theta, and at the 3-4 cell it is 8 minus theta. Now an allocation can never be negative, so what can be the maximum value of theta? As we see, we can choose theta in such a way that 2 minus theta, 7 plus theta and 8 minus theta all must be non-negative, and theta also should be non-negative. This is our requirement, and this can be fulfilled if we can choose the maximum value of theta as 2. If we choose the value of theta as 2 at max, then only all these conditions will be satisfied, and then the allocation at the cell 2-3 becomes 0, that is, it will now become an unallocated cell, it will be freed. So we have the next allocation table like this. Again we find the cell evaluations. We choose E1 equal to 0. Since in each row there are exactly 2 allocations, so we choose E1 equal to 0. As and when we choose E1 equal to 0, V1 becomes 4, V2 becomes 6, then U2 becomes 0, V3 becomes 1, then U3 becomes 8, and it will be then minus 6. V3 will be minus 6. So we will have the cell evaluations as minus 6 minus 9, it will be minus 15. It will be 1 minus 15, that is minus 14. It will be 4 minus 2, that is 2, still positive. Minus 6 minus 4, it is minus 10. It is 4 plus 8, 12 minus 5, that is 7, it is also positive. 6 plus 8, 14 minus 7, it is also positive. So at this stage we have 3 cells with positive cell evaluations. So we have to choose either of these 3 cells as allocated cell. As we see, there are 7 at 2 cells, 3-1 and 3-2. We choose either of them, but if we see that the cost at the cell 3-1 is 5 is lesser than the cost at the cell 3-2, that is 7, so we will make some allocation at the cell 3-1. And here we find the cycle as this one. Here we see that 9 is not a corner cell of the cycle, so we will not make any change at the allocation 9. We will do the change as at the cell 1-1, 12 minus theta, then at 1-2 it will be 4 plus theta, at 2-2 it will be 10 minus theta, at 2-4 it will be 2 plus theta, and at 3-4 it will be 6 minus theta. So again we have the relations theta greater than equal to 0 and 12 minus theta, 4 plus theta, 10 minus theta, 2 plus theta, and 6 minus theta all should be non-negative. Now 4 plus theta and 2 plus theta will always be positive for any non-negative value of theta. So we have to choose among 12 minus theta, 10 minus theta and 6 minus theta, these three, among these three, so that none of these become negative and theta will also not be negative. So the maximum value of theta what we can choose is 6. So we choose theta equal to 6. So the cell 3, 4 will become now a non-allocated cell, that is a free cell. And the next allocation table will be this one. So again we find the cell evaluations. We choose U1 as 0. So V1 becomes 4, U3 becomes 1 and V3 becomes 1, then V2 becomes 6, U2 becomes 0 and it will be 1. Now it is 1 minus 9, that is minus 8, from where this 5 came. It will be minus 8. It will be 1 minus 15, that is minus 14. It will be 4 minus 2, that is 2, still positive. 1 minus 4 minus 3, 6 plus 1 7 minus 7 0 and 1 plus 1 2 minus 9, that is minus 7. So at this stage also we have one positive cell evaluation, that is at the cell 2 1. So in the next step we have to make it an allocated cell. If we make the allocation theta there, then we will choose these cells to make a cycle, and the next allocation table will be as this one. Here we see there are 3 allocations in the first column. So during cell evaluations we choose V1 equal to 0. So U1 will become 4, U2 will become 2 and U3 will become 5. And then V2 will become 2, V3 will become minus 3 and V4 will become minus 1. So the cell evaluations will be 4 minus 3 minus 9. It is minus 8. Four minus 1 3 minus 15 minus 12. It is 2 plus 2 4 minus 6 minus 2. 2 minus 3 minus 1 minus 4, it is minus 5, and 2 plus 5 7 minus 7 0, and 5 minus 1 4 minus 9 minus 5. Now all delta ij's are less than equal to 0, so we have reached to an optimal solution. and we see this solution is different from the solution what we obtained in matrix minima method or in Vogel's approximation method. We find the cost equal to, okay, better we write the solution once again. Solution is x11 equal to 2, x12 equals to 14, x21 equals to 4, x24 equals to 8, x31 equals to 6, x33 equals to 9, yes, and the cost of transportation will be then, cost of transportation is then 2 into 4 plus 14 into 6 plus 4 into 2 plus 8 into 1 plus 6 into 5 plus 9 into 2 equals to how much? 8 plus 84, that is 92, plus 8, 100, 108 plus 30, 138 plus 18, it is 156, which is same as the cost we obtained in the solution through Vogel's approximation method or matrix minima method. One advantage was that we got the optimal solution there at the initial step, and through the northwest corner method we get another solution having the same cost, but we have to improve the solution at many stages. Thus, starting from an initial basic feasible solution, we can improve the solution of a transportation problem to an optimal one.